Good afternoon. It's 1 o'clock Central Standard Time, March the 3rd, 2021. And it's a beautiful day at the Environmental Center. The sun's shining, the animals are out, and the weather is gorgeous. They said it might be up to 70 today before the day's over. That's quite a difference from what we had a couple of weeks ago. We want to welcome you to the STEM Environmental Education Center of the Dallas Independent School District. If you're watching and you have not registered, please do so. Go to www.tiny.cc/EEC register and sign up. That's just for our attendance records. Today we'll do a program called Plate Tectonics. During this virtual field trip, students will explore the historical development of evidence that supports plate tectonic theory and related plate tectonics to the formation of crustal features. Evidence that supports plate tectonic theory will be presented by Ms. Fuller. Mr. Monroe will tell you about Midocean Ridges. Ms. Nash will cover subduction, and earthquakes and plate tectonics will be covered by Ms. Ramirez. You cannot verbally ask us questions, but you can send questions in to www.tiny.cc/EEC-question-answer, and we'll be glad to answer them for you. Now I'm going to stop sharing my screen. And Ms. Fuller is going to tell you all about evidence that supports plate tectonic theory.
Hi, boys and girls. My name is Mrs. Fuller, and this is Terry T, the box turtle. And Terry T is my lab assistant, and Terry T is going to assist in pattern recognition. So if you will look at the plates on the back of this turtle, this is how we can tell it's a box turtle, by looking at the plates. It's a pattern recognition in the human. Let me show you another one. When you were in the 3rd or 4th grade and you started taking social studies, did you ever look at a map of the world and say to yourself, man, South America looks like it could fit right beside Africa? Well, a lot of kids noticed that. Somebody very famous also noticed it. So let me share my screen with you and I'll show you his picture. So the title of this segment is Historical Development of Evidence Supporting Plate Tectonic Theory, How Humankind Uncovered the Fractured Crust of the Planet Earth. Now, I need to tell you that it was not the work of one person, but many, many, many people over many years that came up with this theory. So this is Alfred Wegener. He's from Germany, and he was a climatologist, a meteorologist, he was an astronomer, he was a professor, but he was not a geologist. And that came back to haunt him later in his career. But he looked at the same map that you did, the map of the world, and he noticed that South America fits right beside Africa. And he thought, well, maybe we started out with just one big continent and split into pieces and moved around. And then he looked at fossil evidence, and he looked at rock evidence. There were coal mines in America that matched coal mines in the United Kingdom. There were fossil ferns that matched up with different shores of all these different places. So he came up with this idea of continental drift. He wrote a paper, it's called The Geophysical Basis of the Evolution of the Large-Scale Features of the Earth's Crust. It's kind of a long title. And then he gave 2 lectures to present it. And it was not well received. One of the reasons was they made fun of him because he wasn't a geologist. And they said, you're trying to tell us how to do our work. But one of the other things that he did was he was an explorer, and he explored in Greenland. And before his last trip, World War I broke out. So he was a German, so they sent him to Belgium to fight, and he got shot in the arm. So they sent him back, he recovered. Then they sent him back out. This time they sent him to France, got shot in the neck, and then they sent him back home. Well, he recovered again. So he went on this trip to Greenland, and he was a smoker. And it was such hard work walking through all that ice and snow in that terrible weather that he had a heart attack and dropped dead. And they found his frozen body a year later. So when he died, he was 50. He died in 1930. His work was being made fun of. Then we've got World War II coming along. And the guy that you see in front of you, his name is Harry Hess. Harry Hess, let me see if I can find Harry. Okay, he's a graduate of Yale, and he got his doctorate at Princeton. And he was also working at Princeton, and he was a geologist. And the day after Pearl Harbor, he went down and enlisted in the Navy, and they made him the captain of a Navy attack transport called the USS Cape Johnson. So he was all over the Northern Pacific. Well, guess what was on that ship? A depth finder, something that they could send sound down and find out what was on the sea floor, because he had an idea called sea floor spreading. So what he did was he got contour maps of a huge portion of the North Pacific while he was doing his duty as a captain of this ship. So that was World War II. Well, also during World War II, we had, let's see if she's here. There she is, the most beautiful woman in the world. Her name is Hattie Lamarr. And Hattie Lamarr not only was a very, very famous actress, she was also brilliant. And one of the things that was happening were our torpedoes, as they were leaving our ships to go blow up something, they were being interfered with by the Axis powers. Those are the people we were fighting, and the torpedoes weren't hitting the mark. So she came up with an idea with a musician by the name of George Anthiel, and they developed a radio guidance system using frequency, it's hard to say, frequency hopping spread spectrum for the Allied torpedoes. And this is to thwart jamming by the Axis powers. We said, well, what does that have to do with seafloor spreading and plate tectonics? You'll see in a minute. All right, then the next one, Marie Tharp. Well, what's the deal about Marie Tharp? Well, Marie Tharp was a cartographer. That means that she drew maps. And there was a scientist by the name of Bruce Heezen, and he wanted to go on a research vessel in the Atlantic Ocean and map that ocean. And she wanted to go with the program so that she could map it, and they wouldn't let her on the ship because she was a woman, and they thought it was bad luck to let a woman on a ship. So she had to stay back on shore. And this is in the late 1940s after the war. So anyway, they sent her all the data. She mapped it. She was very meticulous. And her map was published in 1952. And what she found out through her mapping was the Mid-Atlantic Ridge. And this is a part of a system of mid-oceanic ridges that loop all the way around the world. And they made fun of her, just like they made fun of poor old Alfred Wegener. And one of the people that wanted to prove her wrong was a very famous person named Jacques Cousteau. And he sent his little submersible down there, and lo and behold, what did he find? Mid-Atlantic ridges. So that turned out well for her. So Marie Tharp is a very interesting person and crucial to the development of plate tectonic theory. Now, okay, then we've got these concepts of paleomagnetism, plate tectonics, and conduction currents in the mantle. One of the reasons they made fun of Wegener was they couldn't figure out what the engine was that was pushing the continents around. So we had Arthur Holmes, and he's the one who studied and published about convection currents in the mantle. Then we had a Croatian guy by the name of Andrija Mohorovičić, and he's the one who discovered or had the theory about the Mohorovičić discontinuity, which is a break underneath the crust and before the mantle. And underneath the oceanic crust, it's about 10 miles thick, and underneath the continental crust, it's about 60 miles thick. So these guys all had a hand in all this. And for paleomagnetism, the two guys that worked on that were Fred Vine, very famous, and Drummond Matthews. And then we had a guy from the University of Cambridge, and his name is Dan McKenzie. And what he did was he took thermodynamic principles to studying the mantle and came up with a detailed mechanism of crustal movement. So now we know how things move and why they move and all that good stuff. And then we've got the Alaskan earthquake of 1964. Now I remember this, I was in the 7th grade. It was a horrendous earthquake. And a guy, whoops, gotta go back. Well, anyway, a guy named George Flaker, he studied the 1964 Alaskan earthquake, and he was convinced that seafloor spreading was real because he had already studied this off the coast of Bolivia. And so he published in 1965 about subduction. And you're going to hear about subduction in another section. And let's see, okay, we've got that. So the guy in front of you is Jason Morgan. He's a geophysicist. He's from Princeton University. And when he was a very young man, he was the first scientist to use the phrase plate tectonics in a public setting. He was brilliant, did wonderful work his whole career. And what the picture you see is President George W. Bush awarding him with the National Medal of Science in 2003. So, okay, now we're back to Hattie Lamarr. So we're going to see how she makes a connection with plate tectonics. Well, how do you measure this? How far does every continent move? What direction does it move? How fast is it moving? That sort of thing. Well, remember she invented that little frequency hopping spread spectrum for the torpedoes. Well, the scientific community turned their nose up at her invention, and it was not used during Second World War, but it's being used now. And she invented the basis for all modern wireless communication, signal hopping, and it was the precursor to the secure Wi-Fi, which I'm on right now, GPS, and Bluetooth. And that's a little picture there of the GPS, and it's much more accurate for them to measure crustal movement using GPS. Okay, I'm going to get out of this real quick. I've got to show you two books very quickly. The first book is The Great Quake, How the Biggest Earthquake in North America Changed Our Understanding of the Planet. It's by Henry Fountain, the same guy who wrote Isaac Storm. And the second book is this one. Is about Marie Tharp, and it's called Ocean Speaks, How Marie Tharp Revealed the Ocean's Biggest Secret. So I hope you have a delightful day, but I'm going to tell you, this is so fascinating, and both of these books are great. So enjoy studying geology. I'll turn you over to Dr. Gorman.
Thank you, Ms. Fuller. What an interesting lesson. That was really, now the question that came in was some evidence of this plate tectonic. And the basic evidence is on these different plates that are very far apart, yet they have the same fossils and they have the same rocks, and they also have the same kind of dirt and sand. And so that helped them to determine that at one time they probably fit together. Now, Mr. Monroe is going to tell you about the mid-ocean ridges that Ms. Fuller mentioned.
Good afternoon, students. My name is Mr. Monroe, and we're going to be talking about the mid-ocean ridges. And that presentation by Ms. Fuller, you know, I've got all this information about the mid-ocean ridges, and now I know how this information, this data, was accumulated or brought together. In fact, I'm going to get right into a short PowerPoint. You know, the mid-ocean ridges curve like the seam of a baseball on the ocean floor. The mountains in this system lie hidden under hundreds of meters of water. It's amazing that some of the people that she has mentioned had the fortitude and the desire, the determination to do what they did to find out the facts. And that theory of plate tectonics is no longer a theory according to all the evidence that has been brought forth. You know, in a few places, the ridge will poke above the surface. And I will tell you this, the mid-ocean ridges are found in all of the Earth's oceans. So let me go ahead and share my screen with you, and we'll get into this little short PowerPoint. Now, you see that I've got seafloor spreading. And you know what? That is actually the source of the mid-ocean ridges. That's how they were brought about. Mapping the mid-ocean ridges. The mid-ocean ridge is the longest chain of mountains in the world. In the 1950s, scientists mapped the mid-ocean ridges using a type of radar called sonar. Now, this sonar was used during World War II to determine or try to find out where the enemy subs were lying beneath the ocean waiting to ambush some of the larger surface ships. Now, sonar is an instrument that uses sound waves to measure distance. It bounces sound waves off the underwater objects and records the echoes of these sounds. The time that it takes the echo indicates the distance to the object. The scientists found out that the ocean floor was not flat. This discovery piqued their curiosity to discover what the ridge was and how it got there. There are huge mountain ranges called ridges. And as you can see here with the image, that's an image of what scientists believe the mid-Atlantic ridge looks like. Then we have what we call the global mid-ocean ridge system. And you can see in all of the oceans, there are ridges that have developed. We have ridges that are along the North American plate. We also have ridges that are along the Eurasian plate, the Icelandic plate, and just like I said before, they are found in all of the oceans that make up the ocean part of our world. Now, evidence of seafloor spreading was presented by Harry Hess, and you heard Ms. Fuller telling you about him, about Harry Hess. In 1960, he studied Wegener's theory, and that was one of the reasons that Wegener's theory soon became, rather than a theory, it became a fact. Hess proposed that the radical idea that the ocean floors move like a conveyor belt, which in turn moved the continents. This movement begins at the mid-ocean ridge, which forms along in a crack in the oceanic crust. At the mid-ocean ridge, molten materials rise from the mantle and erupt. The molten material spreads out, pushing older rock to both sides of the ridge. Hess called this process seafloor spreading. Molten material, magnetic stripes, and drilling samples supported Hess's theory. In the 1960s, scientists used a small submarine called Alvin to explore the ocean floor. Alvin's crew found rocks shaped like pillows of toothpaste squeezed from a tube, okay, or toothpaste squeezed from a tube. These rocks showed that molten material had erupted many different times from the cracks along the mid-ocean ridge. The Earth is like a giant magnet with north and south pole. The Earth's magnetic poles reversed themselves 780,000 years ago. Rocks on the ocean floor are in a pattern of magnetized stripes. These stripes show when the Earth reversed its magnetic field. Now, this pattern here shows, let me go back. This shows a period of normal magnetism. B shows a period of reverse magnetism. and we can see that there is a difference in the magnetic fields. C period shows, again, a period of normal magnetism. Molten material contains iron. As it cooled, the iron bits lined up in the direction of the Earth's magnetic poles. When the rock hardened, the iron was locked into place, giving the rocks a permanent magnetic memory. Scientists recorded this magnetic memory on both sides of the mid-ocean ridge. They found a stripe of when the magnetic field pointed north and a parallel stripe that when it pointed south. Rock that hardens at the same time would have the same magnetic memory. Glomar Challenger is a drilling ship that recovered drilling samples from the ocean floor. They studied the age of the rock samples. They found that the further from the ridge, the older the rock. The youngest rocks were in the center of the ridge. So there we have it, students. And what I'm going to do, I'm going to stop sharing the screen and get back to the regular screen. And if any of you have any questions about the mid-ocean ridge, remember they are found in all of the oceans that make up our ocean systems in our world. So if any of you have any questions about the mid-ocean ridge, I'm sure that Dr. Gorman can answer those for you. Okay, Dr. Gorman.
Thank you, Mr. Monroe. You mentioned that the mid-ocean ridge was the longest range of mountains in the world. So we want to know how long. And the answer is it's 137,000 miles long. It's the longest mountain ridge in the world. Now, Ms. Nash is going to tell you about subduction.
Hello, welcome to my classroom. Today we're talking about geology, and we're talking now, me, about subduction and orogeny, meaning the formation of mountains. So those plates that we were talking about move and they collide with each other. And when one goes under another, we call that subduction. And that is involved in mountains. So let's look at some pictures here and think about how that happens, because it happens in a couple of different ways, depending on what material is being subducted. So again, here we have our plates. Okay, we just talked about, and they're moving and they're colliding. And right up here is North America right here. And this is the Cascade Range right here, down here, Andes. We're going to be looking at those two mountain ranges. Now, when an oceanic plate collides with a continental plate, the oceanic plate is less dense and it will tend to subduct or go down underneath the continental plate. When that happens, it can create volcanoes. Okay. So this is the subduction plate going down, constantly melting, volcanoes, ash clouds, tsunamis, earthquakes, all kinds of things happen when the big forces collide. So these are called convergent boundaries when they're converging. And again, when oceanic hits continental, so this is the US and Canada. Here's the Pacific Ocean. This is called the Juan de Fuca plate. And it's colliding right here. It's the subduction zone. Okay. And that's what produced the Cascade Range, okay, along here with our big Mount St. Helens and all the volcanic activity and the tallest mountain in the continental United States. Okay. That mountain range is a result of the subduction. Now, farther south, you have another subduction area. the Nazca Plate is colliding with the South American Plate. And this is what created the Andes, okay, big mountain range, that chain of mountains that goes all the way down the west coast here, all the way down to Chile, all the way from Colombia, Bolivia, Ecuador, Peru, all the way down. And if you ever get to go there, it's one of the most amazing places on the planet. Here's Machu Picchu, amazing animals and wonderful people with their little alpaca there. They grow a lot of potatoes. People lived up there, made all these amazing terraces for agriculture, just amazing. Now, convergent boundaries can also occur when two continental plates collide. So when this happens, so we have two continental plates colliding. And again, one is going to go under the other. Okay? And when that happens, it's going to push up some mountains. Okay? So examples of mountain ranges formed by the collision of two continental plates include the Himalayas and the Alps. So the highest mountain on the planet, if you take how high it is above sea level, is Mount Everest, okay, which is 29,000 feet above sea level. That's Mount Everest down here. And the Matterhorn is about a little more than half that, even though it's really tall, but 14,000 feet. The Matterhorn is in Switzerland, Italy, and Mount Everest is in Tibet and China. These are two of the most famous mountains in the world. Let's see. So again, we have two different kinds. One where continental crusts collide, okay, and another where ocean crust collides with continental crust. Okay? And that's what gives us our mountain ranges. Okay? All that movement of those plates. And again, you can see that happening over here is where the Indian subcontinent is crashing into Asian continent. And here's the Cascades. I'm going to stop my sharing right there. Okay, I'm going to stop sharing. Okay, so there's more to learn and amazing mountains to climb. The weird one is that the Rocky Mountains in the middle of our continent don't conform to either of these. And it's kind of a mystery to geologists. What I read that I think is that it's the remnants of an ancient collision. But I don't know. Okay, so if you have any questions, you can ask Dr. Gorman.
Thank you, Ms. Nash. And the question is, at these subduction zones, where one plate is going under the other, how fast is it moving going under the other plate? And it moves between 2 and 8 centimeters a year. That's pretty slow. When you come in science, when you come to time and distance and all, that's kind of mind-boggling. But we think 100 years is a long time. And in science, 100 million years is just average. Okay, now we're going to let Ms. Ramirez tell us about earthquakes and plate tectonics.
Hello, my name is Ms. Ramirez, and in this segment, we're going to be learning about earthquakes as it relates to plate tectonics. So I'm going to go ahead and share my screen with you guys, and then we'll get started. So the first thing we're going to take a look at is a little video of some earthquakes. So as you guys are watching the video, I have a couple of essential questions for you guys. So hopefully by the end of this segment, you'll be able to answer these two questions. So the first question is, what causes earthquakes? And the second question you should be able to answer is, earthquakes occur most often along what boundary type? So think about those two questions as we go through the slides today. Again, you should be able to answer those by the end of this segment. So we're going to go ahead and move over to our next slide. So an earthquake is what happens when two blocks of the earth suddenly slip past one another. So take a look at the diagrams and kind of discuss maybe what do you guys observe or what do y'all notice in these diagrams. And as you guys are making your observations, the surface where the slip is called a fault. And y'all learned about faults in the other segments. So earthquakes can occur along all types of plate boundaries, but they're most common along transform plate boundaries, as you can see an example over here in this diagram. And a transform boundary is simply where tectonic plates slide across or slide past each other. And then as the plates are rubbing against each other, it creates a huge stress that can cause portions of the rock to break. And that's where those earthquakes are occurring. And a good example of a transform boundary would be the San Andreas Fault. And then so our next thing that we're going to take a look at is just a quick review of what an earthquake is. So that answers your first question I asked you guys. And then the next thing we're going to take a look at is how it relates to plate tectonics. So if we take a look at our map of our plates, where do you think you will find the most earthquakes and why? So to help us answer this question, we're going to go to seismicexplorer.concord.org, and it's a online website that will help us understand the role of plate tectonics as it relates to earthquakes. So here we are at that website, and I'm going to move my video down just a little bit. So here we have a key. So you'll notice the size of the circle represents the magnitude of the earthquake. And then the color of the circle represents the depth that the earthquake occurred. And then we can see the color code for plate boundaries and the plate movement. So I'm going to start the simulation. So hopefully you guys came up with a guess on where you think we'll find the most earthquakes. So I'm going to play it and you guys can make your observations. And hopefully you can right away tell that most of our earthquakes are occurring along plate boundaries. Now, earthquakes can occur in other places. It's not totally uncommon, but for the most part, they are going to occur along those plate boundaries. So we're going to go back to our slide presentation. So let me just switch back over here. So to answer your question, most earthquakes are going to occur at or near these plate boundaries. And then we'll go to our next slide. And you might have noticed some of the magnitude differences in that virtual chart there. So this gives you a little explanation of what the magnitudes are. So if it's a magnitude of like 0 to 3, it's just a very minimal earthquake. It's not something super crazy. And then the higher you go, the worse the earthquake is. So you can look at that diagram to help you understand the different magnitude measurements. And then it's measured using what's called the Richter scale. And it was developed in 1935 by, of course, Charles Richter. And it essentially compares the size of earthquakes. So here's like an old school version of what some of the original Richter scales look like. And then now here's the more modern, advanced with technology incorporated into it. So we have a seismograph, or a seismometer is the instrument that's used to detect and record earthquakes. And then we have what's called a seismograph, which is kind of like the paper printout. It's the record that's written by the actual seismograph. And then in our next slide, we're actually going to go to another website to look at an earthquake interactive map. And this is going to show where earthquakes are currently happening. And so I found this to be really interesting because there were actually earthquakes today. I was on the website earlier, and one was actually occurring as I was looking at the website. So this is from the United States Geological Society. And the way this website works, here's our key over here. So the bigger the circle, the bigger the magnitude. And then the color coded is by how old it was. So if it's red, that means it just recently occurred within the hour. The orange ones happened today. So just today, you can see all of these orange dots. Those are earthquakes that have occurred all over the world just today. Oh, no, oh, there it updated. So we can see here where we are in North America, there are actually some earthquakes. There was one in Idaho, and these are again earthquakes that occurred today. Nevada, even one in Texas, in Mentone, Texas. It was anywhere between a 3.2 to a 4.7. So that's interesting. And then Nixon, Texas also had an earthquake yesterday. The second, yeah, that was yesterday. So this is a pretty interesting website, and it's pretty interactive. You can go around and search to look at the different earthquakes that have occurred today and over the past couple of months as well. So that's through the United States Geological Society. So we're going to go back to our presentation. Now, we were looking at examples of where earthquakes occur, and if we take a look at our diagram here, this diagram is simply showing us that the location below the Earth's surface where the earthquake starts is called the hypocenter. So that's a location below the Earth. And then the location directly above on the surface of the Earth is called the epicenter. And then we can even look at this diagram to the right and look at the different ways that the earthquake waves travel. So we have P waves, the S waves, love waves, and the Rayleigh waves. And you can see the different ways that they travel and the different effects that they might have to buildings and things like that. And then our next slide, we have a couple more pictures. See if you can interpret and analyze these graphs. And what do you think the data in these graphs are telling us? And what do you think might be the cause? So this graph over here in the right is the number of earthquakes for central US from 1973 to 2019. So what do you notice about these numbers and the data in that graph? So for me, what jumped out right away is that the number of earthquakes since 2010 has like skyrocketed compared to previously in the early 1970s, 1980s, and 1990s. So what do you think might have caused that? And then to the left, we have a picture of Texas, and then we have some oil wells. And the dots are where earthquakes have occurred, and it's color-coded by if it's a natural, or if it's near an oil well, or if they just don't know what exactly caused that earthquake. So essentially, how does fracking or oil drilling and its waste injections affect faults in Earth's lithosphere? So scientists think that the reason that we have this huge jump of earthquakes starting in around 2010 to now is probably because of an increased use of fracking and oil drilling. So if we take a look at this diagram here, according to the US Geological Society, they're thinking that the fracking itself may not cause earthquakes, but it's actually the subsequent injection of the wastewater into the earth. And so they're actually digging thousands of feet underground and injecting the wastewater from drilling into the earth. And it's believed that that is what's actually causing the earthquakes to happen. And the reason that they're injecting that wastewater into the earth is because they believe it's the safest way to get rid of that waste that's comes as a result of drilling. So I found that interesting. They're still doing a lot of studies to determine the exact impact that this has on our geology, but that was from SMU and the University of Texas. They actually put out several seismographs and things out in the area to do further research. So that's something that you guys can also research on your own, is what exactly is involved in fracking and oil drilling. And then my reflection question for you guys is, why is it important to study plate tectonics? So these are a couple of really interesting pictures. This is from 2018, a 7.0 earthquake in Alaska. So look how much damage it did to that road. And then another one was in China. Now the earthquake itself didn't do as much damage, but look at the subsequent landslide that was a result of the earthquake. So that landslide caused a lot of tons of sediment or soil to just rush downhill, and it destroyed a lot of the homes and buildings in that area. And then, of course, we all remember, well, at least I remember, I'm trying to think of how old y'all would be in 2011, but in 2011, there was the Japan tsunami, and that was caused by an earthquake as well. So it has some pretty devastating effects. So we have the effects of the earthquake, but then we have the other subsequent effects like the landslides and the tsunamis that can also occur as well. And then in 2015, here in the DFW area, there were dozens of earthquakes that occurred around DFW and Irving and near University of Dallas. And it was stated that prior to 2008, there had been no reported quakes, but in the last 10 years since 2015, there had been hundreds of earthquakes. And again, they were like, well, what's causing that and what's the difference? And they were saying that the biggest difference since 2008 is the amount of hydraulic fracking and horizontal drilling. And again, scientists are still doing more studies to help better understand what the effects of drilling and such might be. So that's a little reflection question for you guys. So I'm going to go ahead and stop our screen share, and that's all I have for you guys on earthquakes. And we're going to pass it back to Dr. Gorman, and he's going to answer any questions.
Thank you, Ms. Ramirez. And the question is, have you ever been in an earthquake, and what causes earthquakes? I've been in several earthquakes. I was home ported in San Diego, in California, for about 4 years, and they have earthquakes out there. Now, these are small earthquakes, not real bad. And I was in several of them out there. And also, I was on a mission trip one time in Costa Rica, and they had a pretty good size earthquake down there. And it was kind of funny because I was used to them, so it didn't bother me. But the people that I was with were all from the Dallas-Fort Worth area, and we hadn't experienced any of them yet up here. So they were pretty well shook up. They were pretty scared. But the only damage was it shook things off the shelves and off the tables and stuff like that. No real damage. One of the ones in California did crack a road a little bit, but nothing like the pictures that Ms. Ramirez just showed you. And as far as what causes earthquake, Ms. Ramirez covered it pretty good, but I'll go back over it, reinforce it just a little bit. How does a subduction zone cause an earthquake? Earthquakes occur along fault lines, cracks in the earth crust where tectonic plates meet. They occur where plates are subducting, spreading, slipping, or colliding. As the plates grind together, they get stuck and pressure builds up. Finally, the pressure between the plates is so great that they break loose, and that causes earthquakes. Now, I'm going to share my screen with you. During this virtual field trips, students explored the historical development of evidence that supports plate tectonics theory, related plate tectonics to the formation of crustal features. Ms. Fuller did evidence that supports plate tectonic theory. Mr. Monroe told you about Midocean ridges, and my computer is running out of juice. So I am so sorry, just a minute. Maybe we can solve this, maybe we can't. No, I'm gonna finish it up right quick. Thank you for joining us. If you would, please send in a little form that indicates whether you did appreciate the program or not. Thank you for joining us.